Let's talk about everyday emitters of light: incandescent bulbs, halogen lamps, fluorescent lamps, compact fluorescent lamps, and light-emitting diodes. First, the common incandescent light bulb, still around, but likely a historic relic in coming years. Inside a glass enclosure is a filament of tungsten wire through which an electric current is passed. The current typically heats the filament from 2000 Celsius or 3300 Kelvin, well below tungsten's melting point of 3695 Kelvin. The hot filament emits a continuous spectrum, mostly in the infrared, with visible light as the smaller and useful part. So incandescent bulbs are typically only 10% efficient as light emitters. Here's Lil again showing some incandescent bulbs: a bulb in a flashlight, and a household and Christmas tree bulb. Each bulb has a glass enclosure that prevents oxygen and air from reaching the hot filament, which otherwise would be destroyed by rapid oxidation. Eventually, whether in regular or colored party bulbs, the filament fails because of its gradual evaporation, which leads finally to a break in the filament and to the bulb burning out. Typically, argon is the gas inside the enclosure. If a small amount of halogen element, such as iodine, is added, the evaporation of the tungsten is slowed and the bulb lasts longer. My daughter, Jean Hurrell, shows one of the first smaller versions of a halogen bulb. It's not lit, which is good, because the action of the halogen requires that the whole bulb be hot. So don't touch a glowing halogen bulb. Jean's daughter, Marie, shows a halogen indoor flood lamp. And Marie's younger sister, Cara, shows a halogen lamp now encased within bulbs that can be screwed into standard sockets. Halogen bulbs give somewhat more light and last somewhat longer than incandescents of the same wattage. The common fluorescent lamp that Phil Hurrell shows has been around for a long time. It consists of a cylindrical glass tube with electrodes at each end. Inside the lamp, electrons are boiled from electrodes at the ends of the tube and forced to vibrate to and fro at high speed within the tube by an AC voltage. The tube is filled with very low-pressure mercury vapor added to argon. Mercury atoms are excited by the impact of the high-speed electrons, emitting much of the light in the ultraviolet region. This is the primary excitation process. The secondary process occurs when the ultraviolet light strikes phosphors, a powdery material on the inner surface of the tube. The phosphors are excited by the absorption of the ultraviolet photons and fluoresce, emitting a multitude of lower frequency photons that combine to produce white light. Different phosphors can be used to produce different colors or textures of light. Miniaturize a fluorescent tube, wrap it into a coil, and outfit it with the same kind of plug a common incandescent bulb has, and you have a compact fluorescent lamp, a CFL. Physics teacher Juliet Leogan compares the efficiencies of a CFL with an incandescent bulb with her students, telling how CFLs put out about 4 times more light as incandescent bulbs for the same power consumption. CFLs fit into conventional lamp sockets and have lifetimes more than 10 times that of incandescent bulbs. A downside to the CFL, as with fluorescent lamps, is its mercury content, which poses environmental disposal problems. A more attractive long-term alternative for lighting is the LED. The first light-emitting diodes, called LEDs, to be noticed by the public were those little red lights that tell you whether your stereo or other electronic device is on. These little LEDs have come a long way with flat-screen televisions, or even billboards. Physics teacher Evan Jones points to an extensive use of LEDs in a billboard near his college. The LEDs are arranged in sets of the primary colors, red, green, and blue, and all the colors of the rainbow are activated by turning on various combinations of LEDs. Quite amazing. These weren't around when I was painting billboards in my youth. Here's Evan again, contrasting the common small LED with the larger LED bulb. LEDs have grown in size and now compete with CFLs and incandescent lamps. LEDs are more efficient and last longer. And here's Juliet again, this time including an LED bulb in her student discussion. She emphasizes that whether incandescent bulbs or the variety of fluorescent lamps, it is electrons that do the emitting. Hooray for electrons! Here's LED overhead lighting, and more indoor lighting, and LED outdoor lighting. To learn the details of LED emission, read your conceptual physics textbook. It's all there. Again, these screencasts are to stimulate you to further study. Are you yum with that? I hope so. Here's LED lighting of an arena. Yum. One of the beauties of physics is symmetry. We have learned, for example, that changing an electric field induces a magnetic field, and the reverse, changing a magnetic field, induces an electric field, and the two combined to produce light. So here we have LEDs that convert electricity to light. And here we see the process in reverse. Photocells converting light into electricity on the roof of the Exploratorium in San Francisco. Another of the wonderful symmetries found in physics. Time for a concluding question. First, the lamps we've discussed all need an energy source. Today, most of our energy comes from burning fossil fuels. Years from now, when you're discussing the fact that the primary energy source of the human race back in the early part of the 21st century was burning fossil fuels, will you be proud of that or a bit embarrassed? Until next time, good energy.